Hello everyone, welcome to the lecture 44 in the course Diffusion in Solids. So, last two lectures we talked about the diffusion along the grain boundaries, which is one of the most important diffusion path other than the lattice in the polycrystalline materials, and grain boundary is an important defect which influences the mechanical properties of the material. Another very key defect which is important particularly for the mechanical properties, the movement of which determines the behavior or the mechanical behavior of materials is what is known as dislocations. And today we will talk about the dislocation pipe diffusion. The diffusion can happen along the dislocations also. So, we would see some of the aspects of the kinetic regimes of dislocation, diffusion and average concentration in thin layers. These are some of the keywords that we are going to use. Now, when we talked about initially some revision we did about the structure and defects in crystalline solids. So, there we already talked about what are dislocations and so on. Just to refresh, we talked about what are edge dislocations, where the Burgess vector is perpendicular to this dislocation line, the screw dislocation, where the Burgess vector and the dislocations lines are parallel, and the Burgess vector for let us say FCC can be written as A by 2 110, for BCC A by 2 111, for HCP A by 3 2 bar 0 and so on. The average distance between the dislocations is usually written as K by root of rho d, where rho d is the dislocation density. Dislocation density is nothing but total length of dislocation lines per unit volume. Now, how do we mathematically formulate the problem for the dislocation diffusion? So, like in the case of the grain boundary, we have the Fisher's model. So, taking an analogy from there, Smoluchowski developed a diffusion or a dislocation pipe model for understanding the diffusion behavior through the dislocations. So, basically here dislocations are considered as cylindrical pipe of radius approximately 0.5 nanometer. So, in the Fisher models you consider the grain boundary as a slab. Here the dislocations are considered as a cylinder of radius A, which is approximately 0.5 nanometers. Now, the diffusivity in this dislocation pipe, which is written as d, and the subscript small d is used, which is for the dislocation, it is larger than the diffusivity outside the pipe. Okay, so the dislocation diffusivity, the diffusivity along the dislocation is much higher than the diffusivity along the lattice. So, as I already said that this is very analogous to the Fisher model of the grain boundary diffusion. Now, if C and CD represent the concentrations of the diffuser outside and inside the dislocation pipe. So, C is the concentration of the diffuser outside the pipe, that means it is the concentration within the lattice, and CD represent the concentration of the diffuser inside. So, that means it is the concentration in the within the dislocation. Then you can write the Fick's second law in remember now, because we consider it as a cylinder. So, we have to use the Cartesian coordinates. So, dou C by dou T is equal to D times 1 by R dou by dou R of R dou C by dou R plus dou square C by dou Z square for R greater than equal to A. That means, this is the concentration within the lattice, and dou C D by dou T is equal to D D in the bracket 1 by R dou by dou R R dou C D by dou R plus dou square C by dou Z square for R less than A. So, here R and Z are the cylindrical coordinates. Remember we talked about this that in the cylindrical coordinates r and theta are used instead of x and y, but the z remains the same. Now, the boundary condition which is applicable here are the dou d times dou c by dou r at r equal to a plus is equal to dou d into dou c d by dou r equal to a minus. What is a plus and a minus? A plus means, so this is your boundary if you take the origin from somewhere here in the middle. So, this is your origin. Okay, maybe let me mark it here also. So, this is your r equal to 0 basically, theta equal to 0, z equal to 0. So, this is the origin which is along the center of the dislocation. So, that means a plus is, so this position is a, okay. So, here this position is a, the distance, the radius. So, at a plus means slightly more than a you have the lattice, slightly less than a you have the dislocation. So, to maintain the continuity, the flux should be continuous here. So, then d times dou c by dou r it should be equal to dd times dou c d by dou r. The composition also at the interface should be continuous. So, therefore, c at r equal to a plus, r equal to a minus should be equal to c d. And then additionally, if the dislocation is isolated, then the dou c by dou r, which is the gradient, goes to 0 as r goes to infinity. Okay. So, if you take at a very long distance the gradient, it is goes to 0. Now, here also there are possible to write the initial conditions for the constant source and for the instantaneous source, right, like we have written previously. So, for the constant source z equal to 0 at r at any r and any t, the concentration will be C naught. So, basically it is like the constant source we saw before also. So, where the concentration at this surface is maintained constant. So, at z equal to 0 at any r and any t, C will be always equal to C naught. Whereas at for the instantaneous source, the initially only it will be equal to certain amount, where which is represented by m. So, it is 2m into 2a is what is written, and m is the atomic surface density. Now, the constant source conditions, they are appropriate. For example, if the diffusion occurs from a vapor phase, then C naught is the concentration of the diffuser at the surface in equilibrium with the vapor. They are also appropriate for the solubility limited diffusion, whereas the instantaneous source conditions simulate a conventional thin film tracer diffusion experiment that we have seen previously also at many occasions. So, while the diffusion fields for the constant source and for the instantaneous source are different, we will see that the gradient of log C versus Z plot in the dislocation tail is same for both the cases. Now, again like we wrote in the case of the grain boundary diffusion, the solutions are written like this: C of r comma z comma t contains two terms, C1 z comma t plus C2 r z t for r greater than or equal to a, where C1 represents the concentration in the absence of dislocation, C2 is additional concentration due to rapid diffusion along dislocations. So, actually you can derive certain expressions for C1 and C2 as well, but those are tedious and we are not going to look into that. What is often more important or more practical is what is the mean concentrations. They are of the prime interest for the analysis of dislocation diffusion, like we did in the grain boundary also. And these mean concentrations are what are measured in the serial sectioning experiment. So, remember when you are measuring the tracer diffusivities and so on using the serial sectioning technique, you are cutting the across entire section. So therefore, what you get is the average concentration, not a concentration in a particular dislocation. Okay. So to arrive at the mean concentrations, again we have to use the normalized variables like we did for the grain boundary diffusion, where eta is equal to z by root dt, alpha is equal to a by root dt, beta is equal to delta minus 1 into a by root dt, and delta is equal to dislocation diffusivity by the lattice diffusivity. The d without subscript refers to the lattice diffusivity. So eta basically talks about the influence of the direct diffusion. Beta is the Leclerc parameter, which is a measure of extent to which the dislocation diffusion is enhanced relative to the lattice diffusion. Z is the depth, A is the dislocation radius, and these are the diffusivities that I already told. So for the constant source, if you write in terms of the normalized variable, the average C can be written as C naught times error function of complementary error function of eta by 2 plus pi into A square rho d into Q1. The C2 for the instantaneous source can be written as m by root pi dt exponential minus eta square by 4 plus pi a square rho d into Q2. Okay, so this is for the constant source, this is for the instantaneous source. The C bar is the average concentration here also and here also. Okay, so this average concentration consists of two terms. One is this complementary error function eta by 2 plus pi a square rho d into Q1. What is this Q1? I will tell you shortly. For the instantaneous source, the dependence of the first term is not error function, but it is exponential minus eta square by 4 plus pi a square rho d into Q2. In both the cases, whether it is a constant source or whether it is an instantaneous source, the contribution of dislocation diffusion is proportional to the total cross-sectional area of the dislocations. So, you see pi a square rho d, this is where the contribution of the dislocation diffusion comes into picture. So, whether it is a constant or instantaneous, this is similar. Now, this Q and Q2 are extremely complicated looking functions. As I told before also, the intention is not to ask you to memorize this, but to at least appreciate the mathematical complexity that is involved in analyzing such behaviors, and therefore how hard it becomes when you have additional paths like dislocations or the grain boundaries which contribute to the diffusion. So, this Q in the case of constant source and instantaneous source Q2, these are basically the integral functions where the theta and phi, these are equivalent to y1 and y0. They are the function of y1 and y0, which themselves are the Bessel function, and j1 and j0 for phi, which are also the Bessel functions. So, this is purely to just give you the expression so that you can see the complicated nature of it and appreciate the efforts that go into the solving these diffusion equations. One thing though you can see for the constant and the instantaneous source, the relation for the average mean concentration is equal to minus m by c naught root dt dou by dou eta of c bar into eta comma t. So, this relation you can see when you see these expressions. So, you will be able to at least have some kind of a relation between a constant source and the instantaneous source condition. Although the equations are fairly complicated, you just can see this features. For example, if you plot Q1 and Q2 as a function of eta, you will see that Q1 and Q2 as a function of eta gives you a graph like this, which is a little bit similar looking for constant source and instantaneous source condition. For both of them, it increases with eta, reaches a maximum and then decreases monotonically. Q1, that is the constant source condition, is always positive. It becomes 0 at eta equal to 0, but Q2 is negative for small values of eta. That is because of the rapid diffusion that depletes the diffusers at immediate surroundings of dislocations. Then Q2 also changes sign at the eta value where Q1 is maximum. So here, wherever the Q1 is maximum, this is the position at which the Q2 changes the sign. Okay. So then it is positive at higher eta values. So the diffuser leaking out of the dislocation pipe into the surrounding regions. So remember, like the case of the grain boundary where there is a leakage flux, here also there is a leakage flux. That's why the equations actually become the complicated the way we have seen before. So the leakage of the atoms or the diffuser from the dislocation to grains happen here also. So further, if you separately plot log of Q1 and eta and log of Q2 by eta, this is basically a schematic drawn for the original manuscript. You can refer to this particular reference. So if you plot eta for higher eta, the plot is almost linear. So the log C versus Z is linear for the dislocation tails for the higher eta values. The slopes for constant source and the instantaneous source are nearly identical. So the dou ln Q1 by eta is almost equal to dou ln Q2 by eta, which is equal to minus A alpha by root alpha beta. Beta is the Leclerc parameter, alpha is another dimensionless variable that we have seen before, and A alpha is given by this expression, which is involves integral and the function J naught, which we referred to earlier. Then dislocation density can be estimated by extrapolating to Z equal to 0, and the intersection with the ordinate the C bar reflects the dislocation density. That's why we can extrapolate and estimate a dislocation density. So both in that respect, Q1 and Q2 behave similar. That's what we saw before also, that the dislocation tails have the similar behavior. Now again, although we are definitely interested in the mean concentration, but even a more practical thing for us to consider is what are the kinetic regimes of diffusion. So like the case of the grain boundary, we also have the Harrison's regime for the dislocation diffusion as well, and the fundamental concept is similar, that this occurrence of a particular regime depends on the average dislocation distance and the lattice diffusion length. That means how much is the lattice diffusion inside the lattice that is happening, and how much is the diffusion happening in the dislocation through the dislocation, and what is the average spacing between them. So the type A kinetics for the long diffusion anneals and high dislocation densities. The high dislocation densities means these are very near to each other. So in that case, when they are very near to each other, then for example, if you are here, then this has a contribution of the diffuser coming out of this dislocation as well as this dislocation, as well as the coming from directly from the lattice itself. So therefore, you cannot distinguish a concentration at any particular point, whether it is coming as a leakage flux of one dislocation, as a leakage flux of another dislocation, or it is coming directly from the lattice through the lattice diffusion. So, in such a case, what you actually effectively measured is a effective diffusion coefficient. This regime is applicable for higher diffusion temperature and higher dislocation densities. This D effective can be written as lattice diffusivity into 1 plus pi a square rho d, d of dislocation by d minus 1. If the dislocation density and the lattice diffusivity, let us say, are equal, then you can see it here as well. The B kinetic regime, so just one more point, this type A regime is observed when this lambda, this is capital lambda, is less than root dt. Remember, lambda is the average dislocation spacing, so distance between these two. So, if this is very less than the diffusivity along the diffusion depth just along the lattice, then you get the type A regime. The type B regime is observed when the lambda is far greater than root dt. That means the dislocation are more spaced out and they are enough apart for individual diffusion fields to not overlap. So, here in this case, if you are here, then it can be distinguished that this is coming because of this dislocation, the leakage from this dislocation, and these fringes do not overlap. And the slope of the dislocation tail is given as dou ln c bar by dou z equal to minus a alpha by root of d divided by d minus 1 into a square. So, this a is weakly dependent on alpha, and the slope can be directly found from this, and this delta is equal to dd by d, which is determined by the slope of the tail if alpha is known. Commonly you assume, if A is known, commonly you assume A is equal to 0.5 nanometers for metals, whereas A is larger in ionic crystals, of course, because of the electrostatic effect. Here, if you compare this type B regime with the type B regime of the grain boundary diffusion, there are a couple of things that to note. That first is the tail shape. In the case of the dislocation tails, it is linear in log C bar versus Z, whereas the grain boundary tails are linear in log C bar versus Z to the power 6 by 5. So, this is another very important difference when you have to figure out or distinguish the dislocation diffusion as well as and the grain boundary diffusion. So, this is linear in log C bar versus Z, whereas grain boundary is log C bar versus Z to the power 6 by 5. But remember that if you want to see this difference very clearly, remember this Z is power 1, this is 1.2. So, if you want to measure this difference very clearly, then at least 2 orders of magnitude in the tail measurements are required. That means, the tail should, so what we mean by the 2 orders of magnitude in the tail measurements is required is that the activity or the concentration should drop, so that you have a sufficient slope for the statistical estimates to occur in a reliable manner. Another important feature is the time dependence. The dislocation tail slopes, they are nearly time independent due to slow variation in A alpha, whereas the grain boundary tail slopes are proportional to t to the power minus 4. That means, the log C bar by dou log C bar by dou Z to the power 6 by 5 are proportional to t to the power minus 4, minus 1 by 4. So, this is a sensitive test to differentiate between the dislocation diffusion tails and the grain boundary diffusion tails. The diffusion along the isolated dislocation, and they are grouped in LAGP. So, basically, a lot of times when you want to distinguish the difference between the dislocation tails and the grain boundary tails, whether it is coming from where, then you do at the same temperature certain time dependent measurements. So, if it is really grain boundary diffusion, then you can capture the slopes are proportional to the t to the power minus 1 by 4. And lastly, in the kinetic regime C, this is probably the simplest to understand, where the lattice diffusion is almost 0 and the entire diffusion takes place through the dislocations. So, here the penetration profiles are linear in a log C bar versus Z square plot. This is like your typical Gaussian curve, where so the dou ln C bar by dou Z square for the dislocation tail will give you minus 1 by 4 dd into t. So, with the slope you can directly determine the dislocation. But like I said, for the grain boundary also, in here also, although the C kinetic regime looks very easier to understand mathematically, the performing the experiment in the C kinetic regimes are very difficult, because the diffusivities are low. So, the only diffusion that is happening is through the dislocations, and therefore, the concentration that you have to detect are extremely small, and that is where the high precision techniques are required to actually measure the dislocation diffusion in the C kinetic regime. So, with this we will end today's lecture, and we will continue with the tutorial in the next lecture. Thank you.